Hello students, welcome back. In the previous video, we covered up to the definition of the derivative. Basically, it was the instantaneous rate of change. We could express it as the average rate of change formula with limit b is approaching to a, or equivalently, Newton quotient, where limit h is approaching to 0. These two are equivalent, and we can see the equivalence algebraically like this. The change of variable h is equal to b minus a, and flipping a to the other side, we get b equals to a plus h, and apply these to this quantity here. b minus a in denominator, that's equal to h, and b in this numerator is equal to a plus h. If you do that, you get the second quantity. So they are the same. Furthermore, there is a graphical justification like this too. We have the same graph, y equals to f of x, and same secant line, and consequently the same slope, but labeled differently, b comma f of b versus a plus h comma f of a plus h. After all, b is equal to a plus h. If you use the first graph, we get this expression as the rise over run, the difference of y coordinate f of b minus f of a over the difference of x coordinate b minus a. If you use the second graph, we're going to get the next expression. Difference of y coordinate is f of a plus h minus f of a, the numerator, and the difference of x coordinate is a plus h minus a, that's h. So that's the denominator. Consequently, these two are the same. And so much for the review. Now let's go from here. These equivalence expressions is about the derivative, and that derivative was for fixed value x equals to a. Now let's consider the situation where x is moving around, not fixed as a, but moving around. In that case, in this expression, instead of a, we're going to get x, and that's changing, so you're going to get a bunch of derivatives, or more precisely speaking, a function that consists of the derivatives. That function is called the derivative function, and here is the definition. Please compare this definition with the second expression in the definition of the derivative. This is a number because x is fixed as a certain number a, and this is a function because x is moving around. Otherwise, exactly the same. Now, is it possible to develop the definition of the derivative function using this? Yes, it is possible. We're talking about a, so replace a by x. About b, well, we can either leave it as b or create another character. There are various different ways, but most of the time, students get even more confused, so textbook authors generally avoid it. I'll do the same thing. Our textbook author uses only this one, and I'll do the same. This is the definition of the derivative. Okay, we went through the definition of the derivative and that of the derivative function. Let's do a computation problem. Copy and paste the derivative formula here, and then let's use these formulae to calculate the derivative. For example, this one. How do we do that? Well, you can use this formula first and then this formula a bit later. Method number one, we can use Newton's quotient formula here. Let's calculate this quotient, simplify, and then we're going to take the limit. Here we go. And let's increase the font. Okay, this is a function, and then we need a plus h, so plug that in, and you're going to get this expression, 1 plus h total quantity squared plus 1, and then f of 1, plug in x equals to 1. That's the numerator. That's this part. Denominator is always h. Simplify by breaking up parentheses and then crossing out the constants. In the end, this is what we get. And unless you made a mistake, you can factor h out, or the constant will be gone. and that and the denominator cancel each other out, you're going to get this kind of expression. In this particular case, 2 plus h. H is going to 0, so the limit is 2 plus 0, that's 2. Another way to handle it, we can use this. F of b minus f of 1 over b minus 1, and for x equals to b, plug it in, x equals to 1, plug it in, subtract one from the other and simplify. What do you get? We ended up with b squared minus 1. So it can be factored further. After simplification, we got b plus 1. b is going to 1, so the limit is 1 plus 1, so we ended up with the same answer again, 2. There's a bit of a difficulty in the second method. This problem is kept as quadratic, so from this expression, it wasn't too difficult to factor it. Now for higher order, that factorization may be rather big trouble, pain in the rear end. How about the second problem? Similar, very similar, so I'll just show you and then let you go through this. Here a value is -1, so Newton quotient looks like this. -1 plus h minus this g of -1, plugging in -1 plus h into x, we get that expression, and break up parentheses and simplify, factor h out and simplify. In the end, we get h minus 5, which goes to 0 minus 5. Equivalently, put everything into this. Plug in b, plug in -1, and then break up all the parentheses and simplify. We get this quadratic in the numerator. Simplify, we get something like this. And further, we get 3 minus b, like this. And then take the limit. B is going to -1, so we end up with -5, the same answer as before. You may have an illusion that this is going to give you a simpler computation, but usually it's the other way around. This one is easier because this factorization over here is most of the time not so easy. But if you use Newton quotient, that's easy. You can always factor h out, and that's it. Okay, so much for the computation. In the future, we're going to be using the formula method. Okay, now, from now on, let's go over to something theoretical, and we are going to state and prove this theorem. If a function f of x is differentiable, or the derivative exists there, then it is continuous there. This theorem is rather deep, so if you're not really interested in the proof, stop here and then just skip over to the next video. It's okay, you're not going to miss too much. But if you're interested, and also if you're interested in mathematics as your future major or minor, or you're just exploring, then please stick around and see if you find something you like. Okay, here we go. Basically, this is what we want to prove. Differentiable means the derivative exists, so this limit exists, and that quantity has to be a real number. So if this is true, then this is continuity. The limit exists and function value exists, and they're the same. So this is differentiability, and that's continuity. Alright, we are trying to prove this one. We are trying to prove this one. So let's begin with manipulating the conclusion a little bit, so that we can actually prove it. Minimal manipulation. Flip this f of a to the other side, and then let's write it as equal to 0. So this limit equal to f of a versus subtract f of a, then this difference is going to 0. That's equivalent, isn't it? Okay, how do we prove the second? Here is an ingenious trick. We divide and multiply by the same quantity, x minus a. And then we use the limit rule. Limit of this times that. Okay. So limit of this times limit of that. It's just a limit rule. We can do it as long as both limits exist. The blue limit is easy. This is going to 0. X is going to a, so this is a minus a, that's 0. The red limit, if it exists, is a derivative, f prime of a. So what do we have? F prime of a times 0, so overall quantity is 0. That's precisely what we wanted, right? One may wonder, wait a minute, why is this necessary? Because this blue is 0 anyway. 0 times something is 0, so why do we have to have this limit? Well, the answer is, if this limit is something like infinity, growing much faster than this going down to 0, then the product will not be 0. If this limit does not exist at all and it fluctuates badly, again, this limit may not exist at all. So something times 0 is always 0. That's not always true. That something is real number, then yes, that's true. But we're talking about the limit. So limit may not be a real number. And that opens up a can of worms. Okay, that proved the theorem. Differentiable, then continuous. So if you have a discontinuous function, then differentiability is out of question. Okay, we went through something deep. Alright, let's take another perspective, and you can regard it as a kind of reward for the student who stayed up to here. Okay, let's look at the derivative notations, and these notation, putting primes for the derivative, double prime for the second derivative, derivative of derivative, triple prime as a third derivative, derivative of derivative of derivative, and so on and so forth, and times, and further. That notation was developed by a mathematician called Joseph Louis Lagrange, and he worked in France, but as a matter of fact, he's Italian. He was born in Italy and studied in Italy. He worked in France, so it is well known in France, but he's actually Italian. So this can be regarded as an Italian notation, arguably French notation too, because after all, he worked in France. And this one is German notation. The derivative, the second derivative, and so on, and it is by Leibniz, this person. And I'm afraid this is more complicated than previous notation, but there's no way around. This is widely used, and then our textbook author uses this one as well, so you gotta know both of these two notations. Whenever I try to use Leibniz notation, this dy dx notation, and students get alarmed and they get confused, but it can't be helped. There's no way out. And these notations were developed separately for hundreds of years, and then they are now stuck, so nobody can change it anymore. You just have to learn them all. Next notation. Our textbook author doesn't deal with this, but it is very, very useful in a lot of other regards, in higher level maths too, but also in computer algebra system. It is by Euler, a Swiss mathematician, this gentleman here. And then finally, putting dots on top of a character, that's by Newton, the most famous of all these people. So here's a project, and go through these sources and then get a brief report on each of those people, or just pick one and then do write some report about their contribution in calculus. Any kind of report, maybe a couple of pages, maybe longer, maybe shorter, whatever it is. Submit it and I'll give you an extra credit. That's a reward for staying this long, a free extra credit opportunity.